Hello, y'all. This is Darrell Lee Berry Jr. back with some more linear algebra, and we'll continue from the example we started on yesterday. And you know it, right now my tab froze. Let me open it back up. Well, we're going to do this example here, which is still in section 4.4, example 3, and we'll start from there. Okay. And okay, let's skip. So we have, considering the function d, I'll take d to be a derivative, differentiation map, P3 to P2, and d of f is f prime, and we know that we can do a prime to make a derivative. And the constant function 1 gives a basis for the kernel of d, because d of a constant equals 0. So d of the constant gives a 0, so it's in the kernel. The image is P2, because the transformation of P3 is P2, using the definition we did earlier. So the image, W, is in the subspace W, and W is the transformation of V. So if you transform P3 with a derivative, it becomes P2. Therefore, P2 is the image of that transformation. So that makes sense. That's simple enough. They give us an example. Given GT equals A plus VT plus CT squared, and that's in P2 because it's the polynomial of the second dimension or degree, and f of t is at plus 1/2 bt squared plus 1/3 ct cubed. So we just took the integral of that. That's in R3. And df equals gt. So dp3 goes to p2. Thus, this is the image, or in the image. Okay, so B, that was A. B says, instead of the linear map M defined in 2A with the interval, so now they're giving us an interval equals 1, 2. If F is in the kernel of M, meaning F the transformation of M onto F equals 0, then that equals F in COI T F C equals 0. And that's for all, and they're given an interval 1 to 2. So the transformation of f equals 0 if f is in the kernel, which is the definition basically. And that's why it says we must have f of t equals 0 for all t and I. Given any continuous function g, we can take f of t equals g of t divided by t. And this too will be continuous since f equals g. We see the image m equals COI. So the image of m, so all of the results of the transformation of a function that gives 0 is in the image of I because it's the result of the transformation. It's just also in the kernel. We actually read it to explore in exercise 15 what happens for an interval I containing 0. So it seems like it'll be the same thing. I'll adjust this slightly. Right. And C, consider the linear map P, P2 to R2 defined by P F equals F0, F1, then the kernel of T consists of, so we have a linear map, the polynomial 2 to R2 divided by the transformation is the function inputting 0 and the function inputting 1. So the polynomial is just something with a variable, and the transformation is to put 0 in for the variable and make that the first component of the vector and 1 in for the variable, make that the second. Then the kernel of T and the kernel consists of all quadratic polynomials or roots at 0 and 1. So it says the kernel of T, the things that's in that when you transform it, it gives you 0. So the kernel is what you transform to get 0. So I don't see how it can have a root of 1 and equal 0. Oh, I see. So they're saying kernel of T if f t equals t minus 1. So I'll just swap the order of that is all roots t equals 0 and or t equals 1. So if I put in 0 for t, then of course it just multiplies to 0. If I put in 1, then 1 minus 0 is 0. So I just swapped the order of that and it made more sense to me. So f of t is a basis for the kernel of t. On the other hand, given any AB in R2, we can set ft equals AB minus AT. On the other hand, given any AB in R2. So I'll just say also instead of on the other hand, if you have an interval AB that's in R2, I guess not an interval, but a vector or point can set f of t equals a plus b minus a t, and t f equals a b. So now they're just picking a different function. Those are not necessarily connected. Interesting. All right. So we'll do the last few of these. So we have C, D, and E. So we're on C at the, excuse me, D at the moment. So we'll do these last two, then I'll take a break. So modifying the preceding example slightly, consider the linear map S, which is a second degree polynomial, and we're transforming that into R3, defined by SF equals F0, F1, F2. So the kernel here, the kernel of S is the zero vector. Since a non-zero quadratic polynomial can only have two roots. So sounds like they're talking about a plus bx squared plus c x plus c. So it's a plus bx plus cx squared. Right? On the other hand, it follows from the Lagrange interpolation formula, theorem 6.4 of chapter 3, that for every a, b, c in R3, there is a polynomial f in P2 with S L equals A, B, C. So it's saying that every polynomial, you can get to it by this transformation. Excuse me, every polynomial you can put into this transformation to get to this R3. So it's giving us a formula, f of t equals a over 2 t minus 1 t minus 2 minus vt t minus 2 plus c over 2 t minus 1. Right, so I'm not sure why they did that. So why don't we go to chapter 3 and see what theorem 6.4 is? I'm sure this is 6.4. Right? So the Lagrange interpolation formula. I'll make an aside for this. And it did say Lagrange interpolation, right? Just making sure. Right? So it says given k plus 1 points, given k plus 1 points, P1, B1, P2, B2, T k plus 1, B k plus 1. In the plane with T1, T2 all the way through Tk plus 1, distinct, there is exactly one polynomial P. So you have distinct T1, T2 all the way to Tk plus 1. There is one polynomial P in Pk whose graph passes through the points. All right? So you have these points. T1, B1, T2, B2, all the way to the Tk plus 1, Bk plus 1. In the plane, every T value is distinct. So there is exactly one polynomial whose graph passes through each of the points made by these. So simple enough. So let's go back to where we were. All right. So now we have that. So this was coming from this for every A, B, C in R3, there is a polynomial f of the second degree that goes through these points. All right. And that's where they get the explicit form from. All right. The last one, E, it says what happens if we consider instead the linear map S prime polynomial first degree to R3, defined by the same formula. Here we're restricting the domain of S to the polynomials of degree at most 1, which is what the P1 is. Surely, the kernel of S prime is the 0 vector, because there's only 1 degree, which is like X. So the only thing, so if you take the derivative of that, it equals 1. So the only thing that will make that equal 0 is if you put in X for 0, 0 for X. But now which vectors A, B, C are in the image of S? This is a capital image of S. We leave it to the reader to check that A, B, C is in the image of S if and only if A minus 2B plus C equals 0. Once you know, they will leave it to the reader. I'm starting to hate this book as we get farther along in the book. Understand the reasoning behind this, that there's a formula or at least a polynomial that goes through each of those points, just like we saw with the Lagrange interpolation. But I don't see specifically how they got this exact polynomial. I'm trying to see if I see a pattern. I don't think I do. Because there's a 1/2 here, 1/2 there. There's a t minus 1 times t, a t minus 2 times t, but a t minus 2 times t minus 1. So, right, well, maybe we'll come back to that. This is reviewing some terminology from the blue box on page 88. We say that the linear map T from V to W is on to or surjective when the image of T equals W, right? So we have some new terminology here, or we hash terminology. So surjective T V to W and T image T, which means that when you do the transformation T, the values that put it in W. So this is like saying the transformation of V gives you the image, and it's saying that these are the same. So it's surjective, right? And I'll write surjective a bit better. Surjective. So V maps onto W. Right, so it's a good place to stop. I'll probably be back later tonight to continue through these and maybe do some problems or more examples. So thanks for joining. Like, share, subscribe, and I'll see you next time.